Okay, now let's take this model, linear programming model, LP model, that we developed and try to find the solution that maximizes the profit subject to these constraints. Remember, these two are labor hour constraints, these two are sales constraints. So when you have only two variables, then we can solve this using graphical method with one value of one variable represented by the x-axis and the value of the other variable represented by the y-axis. If you have more than two variables, then you cannot solve using graphical method. Okay, so let's first look at generally what's going on. So we have graphical method. So we're going to represent the x-axis with x sub 1. Okay, and we'll use y-axis to represent x sub 2. Now let's try to understand how the profit works here. The net profit we modeled as 80 x sub 1 plus 129 x sub 2, right? Suppose we want a net profit of 103,200. Okay, we can get that net profit by producing 1290 of x sub 1 and nothing of x sub 2. So that will give you a net profit of 103,200. That same 103,200 you can make, okay, by producing nothing of x sub 1 and 800 of x sub 2. So that also will give you a net profit of 103,200. So it so happens that if you connect these 2 points with a straight line, okay, now all the points in this straight line each point represents a particular combination of production. Okay, like for example, if you take that point, that's about roughly 800 units of x sub 1 and maybe 370 or 380 units of x sub 2. Okay, whereas if you look at that point here, that's about 400 units of x sub 1 and about 600 units of x sub 2. Now what is unique about this line is, since this point gives you profit of 103,200, that point also gives you a net profit of 103,200. That's the entire line. All the points on this line will give you exactly $103,200 in profit. So for this reason, this line is called ISO profit line. Now our idea is, okay, so we take that line and we want to increase profit. Okay, as long as you don't change the slope of this line. Okay, if you change the slope, then 80 and 190 will no longer hold. So we want to maintain this. You can't change the profits for these two variables. So as long as you don't change the slope, our idea is to increase this line as much as possible away from 0. Okay, and of course there are restrictions. You can't just simply keep on increasing this line, this ISO profit line. So we have to then start with the constraints. Okay. So we have assembly hours constraint. So let's take assembly hours constraint first. And the way to identify all the points that will satisfy the assembly hours constraint is to first look at what this expression will look like when it is equal to 10,000. When the left hand side is equal to 10,000, what would that look like in the graph? Okay, so we set it equal to 0, equal to 10,000. Okay, now to draw and that would be a line, right? 5x sub 1 plus 6x sub 2 equal to 10,000 will be a straight line. The easiest way to draw the straight line is to set one value equal to 0 and find what the other value is. So if you set x sub 2 to 0, okay, and you solve for x sub 1 such that that will be equal to 10,000, you will get x sub 1 as 2000. So x sub 1 equal to 2000, x sub 2 equal to 0 is one point that will satisfy this constraint by exactly being equal to 10,000. You do the other way, like set x sub 1 equal to 0 and solve for x sub 2. Okay, so that will give you x sub 2 equal to 1666.67. It is that point. Now if you connect these 2 points, then you will find all the points that will satisfy, or all the different combination of values for x sub 1 and x sub 2 that will satisfy this constraint by being exactly equal to 10,000. But our constraint is not exactly equal to 10,000. Our constraint is to stay less than or equal to 10,000. So what this line does is it takes the entire feasible region. So this is the feasible region when we start out with. Because remember, x sub 1 has to be greater than or equal to 0. X sub 2 has to be greater than or equal to 0. It is the first quadrant that we're talking about. Now it bifurcates this area into 2 sets. One set of points that is feasible, the other set of points that's infeasible for this constraint. And in this particular case, it is easy to see this side is feasible because this is the smaller side and that's the larger side. So any point that falls outside this line here is this left hand side is going to be greater than 10,000. That would make it infeasible for this constraint. So any point to this side will be less than or equal to 10,000 and that will be feasible, and any point on the line will be exactly equal to 10,000 and they will also be feasible. So that area is feasible for assembly hours. Okay, but that's not the only constraint we have. So we have the testing hours constraint. So now we'll keep this because we need to stay within this area now. So let's take testing hours constraint and do exactly the same thing. Let's set it equal to 3000 and draw that line. And to draw that line, we need 2 points. We'll set x sub 2 to 0 and find what x sub 1 should be, which will be like 3000. So if x sub 2 is 0, then x sub 1 will be 3000 and that is represented by that point. Now if you set x sub 1 to 0, then x sub 2 has to be 1500 and that would be that point. Now once again, when you connect these 2 points, you will find all the values of x sub 1 and x sub 2 that would give you 3000 for this constraint. So all the points here are feasible for the second constraint, and anything that is below the line are feasible for this constraint. Any point above the line are not feasible for this constraint. Now remember, we have to satisfy both the assembly and the testing constraint. So for assembly, this set is the feasible region. So now when we bring in this second constraint, that divides the previous feasible region again into 2 parts. One part is still feasible. The other part is, while it's feasible for the first constraint, this is no longer feasible for the second one. So when you bring in the second constraint, the feasible region becomes a little bit smaller. Okay, and now at this point, all the points in this area will satisfy both the first and the second constraint. See, these points satisfy the first constraint but not the second. These points satisfy the second constraint but not the first. Now these points satisfy both the first and the second constraint. Now we have 2 more constraints. So let's bring in the third one, which is x sub 1 less than or equal to 1000, the maximum that we can sell of x sub 1. So which means you set x sub 1 equal to 1000 and x sub 2 you don't care. So all points on a vertical line, okay, will satisfy x sub 1 by being exactly equal to 1000, and since we need x sub 1 to be less than or equal to 1000, now these points are feasible and these are not. So now the feasible region after the first two constraints are now being further subdivided into ones that are feasible for the third constraint as well, and the ones that are not feasible for the third constraint. So we have to now eliminate that part. So we, at this point, this is the region that is feasible for all the three constraints. Now the last constraint, x sub 2 less than or equal to 1000, again set it equal to 1200, set it equal to 1200, so that is x sub 2 equal to 1200. Now draw a straight line, and that straight line will represent x sub 2 equal to 1200, and that again further subdivides the feasible region that we had for three constraints into ones that are feasible for all four constraints and the one that's not. So now we have determined the feasible region. Okay. So we have constraint here. Okay, that's the first line. This is the second line. This is the third line. That's the fourth line. Okay, and this is your feasible region that satisfies all the four constraints. Now you see this blue line is outside the feasible region. So that means that this blue line is a redundant constraint. Okay, this constraint is not reducing the feasible region any. So you can just throw that constraint out. That constraint will always be satisfied if these three constraints are satisfied. Okay, so we don't need to worry about that constraint.